In this video, we shall discuss some properties of probability generating function. Here is the definition for quick reference. Now, the first and foremost thing that you should observe is that if I put t equal to 0, then this sum is just a finite sum. It contains only the very first term and nothing else. So, xi t must always converge at t equal to 0. The second thing that you can notice is if I put t equal to 1, in that case, what do I have? Xi of 1 is, I will write down the sum, 0 to infinity, pi. Now all these things are 1, so I just write pi. And I know that sum of all these things is equal to 1. So I have my next property. Now the third property will again use the same idea. I saw that if I put 1, I will get 1. Okay, now I will try to put minus 1. Let's see what happens. If I put minus 1, in that case it will keep on being plus 1, minus 1, plus 1, minus 1 like that. So it will become 0 to infinity pi, then minus 1 to the power I. Observe that this must converge because pi's are all non-negative, so the only sign comes from this. So once I take its absolute series, I get back to this because the effect of the sign goes away. So the absolute series converges to 1. If the absolute series converges, then naturally this series must also converge. So for t equal to minus 1 also it must converge, though I may not have a ready description for this limit, but at least I can say that it will converge. Now suppose I put something in between. Suppose I put half. What can you say about this? It will definitely be less than this, because if pi times 1 that converges, then it is half, half square, half cube, etc. Those are obviously less than 1, so it must also converge here. Similarly, if I put something negative, then also thinking about the absolute series, you can see that the absolute series must converge. So, for any number between minus 1 to plus 1, if I take t anything in between, I am sure that this series must converge. Because the worst possibility is when I put 1, that is the largest thing, it converges for even that. So for anything which is smaller than that, we will also have convergence. Because if t is between, absolute value of t is between 0 and 1, then powers will become even smaller and smaller and smaller. So I have my third property. The PGF must exist or must converge for t in minus 1 to 1. It may converge for other values also. For instance, we saw an example where it converges or exists for all real values. In case of the geometric half, we saw that it exists for open minus 2 to open 2. But this one is guaranteed for any random variable taking nothing but non-negative integer values. I am sure that the PGF must exist in this interval. It may exist outside the interval as well. Now, if we want to use the language of power series, then for this power series, the center is at 0, and I have said that I must converge over everything within a distance of 1 from 0. So I can state this same result as its radius of convergence must be greater than or equal to 1. But if you do not know this term power series and radius of convergence, do not worry. This is just the thing that you should remember. For t from minus 1 to 1, xi t is guaranteed to exist. That's all. If you know this language, this is just a restatement of this property using that language. The fourth property is something that we cannot prove in this video. It comes from a general property of power series that xi t, which we know is defined for t in -1 to 1, is actually differentiable as many times as you like. If I differentiate it once, twice, thrice, 10 billion times, it's always differentiable. And you can differentiate it term by term. Now let's understand what is meant by that. Here is the series defining xi t. Now I want to find its derivative, first derivative. How would you go about it? If it is just a finite sum, then naturally you will differentiate this, which will give 0, differentiate this, which will give p1, this will give you 2p2t, 3p3t square, and stop. But now I have an infinite series. Can I differentiate term by term this entire infinite series and can write that this is also ... Well, if you just think naively, you might think, oh, this is the most natural thing, but that requires a proof because this infinite series is actually a limiting process. You are taking a limit. When you are doing differentiation, that is another limit. In this case, I am first taking the limit of the sum, then I am taking the differentiation limit. In this case, I am differentiating first and then I am taking the summation. So the limits are being interchanged. Limits sometimes may change if you interchange them. In this case, that problem is not there. That is why I say it is differentiable term by term. So if you just carry this process out blindly, you are guaranteed to have the correct result. And as I said, any number of times, so if you want, you can differentiate this once again and you will get, these are not there, 2p2, then 3 times 2, p3, etc., etc. So you can get all the subsequent things. So you can see that it is 3 times 2, then it will be 4 times 3 and things like that. And what are the possible values of t? I am still always working for t from -1 to 1. I know that PGF at 0 must take the value P0. So here I am showing xi t and here I am showing t. So it must pass through this point. Also at 1 it must pass through 1. So these 2 points must be there. I also know that it is differentiable, so in particular it is continuous. So it must be some kind of a continuous curve between them. I am going to give you a number of such curves and you have to tell me which are the ones that are impossible. The first graph is like this, goes down then comes up. I called it 1. The second curve is much like this, but it never comes down. It just goes up like this. The third graph is just a straight line. The fourth graph is much like 2, but it is going up and then coming down. This one goes up beyond 1 and then comes down. You have to tell me which of these graphs are actually impossible. So think of the derivatives. And I will quickly remind you that all the pi's are non-negative quantities and at least one of them must be strictly positive because the total probability has to be equal to 1.